This video will cover the notes for the first extra credit assignment and fill in all the examples that show up in those notes. We'll cover solutions for those and what those should look like. About the first 3/4 of the first page is stuff that actually also shows up in the notes for Chapter 5. I reproduced it because it was relevant here too. Where in Chapter 5, this would have come up as sort of a lead-in to when we ended up talking about the normal distribution, where there were some more general probability things that we started off with. It's some of that, where the first big thing that's there is the distinction between a discrete and a continuous random variable. And the normal distribution is a continuous random variable. And if you just think about what its graph looks like, it's a bell curve. Right? The important thing being it's a curve. It's all connected together. And that's what a continuous function should look like. Right? You graph a continuous function. It should all connect together. With a discrete variable, you don't get that. A discrete variable really would be discontinuous everywhere. So if you graphed it, you would have a bunch of dots. You'd have a bunch of disconnected dots in your graph. And discrete variables are what we're going to be concerned with for this extra credit assignment. And as far as how many possible values there can be, you could have a discrete variable with a finite number of possible values, but you could also have a discrete variable with a countably infinite number of possible values, which just means that you could enumerate them. Like you could figure out what the next possible one would be, but then there would be no upper bound, something like that. We're going to really just kind of focus on ones that have a finite number of possible values. And to start off with, if you have a finite number of possible values, you could display the distribution in a table where you could have all the possible values in the first row and their probabilities in the second row. Can't get away with that with a countably infinite number of possible values because you've never finished making the table. But the beginning of the second page has this there, where there's this table where you have the possible values in the top row and then the probabilities in the bottom row. And then the examples that are there in the second page are really all going to be based off of what's there in that table. So that example on the second page, it's about how many times a randomly selected high school student would take the SAT. I suppose, presumably in an area where the SAT is the more popular one. But we've got the distribution here, which I just kind of reproduced from the page. And then we want to get a couple of compound probabilities, where a compound probability is just a probability that would involve multiple possible outcomes. So this first one, the probability that x is greater than or equal to 2, I think your intuition is going to be right here, because what you're going to do is you're going to think, well, what possible values are going to satisfy this inequality of being greater than or equal to 2? And you look at the table, 2 is going to work because it's greater than or equal to 2. 3 works, 4 works, and you add those probabilities together. That's exactly what it is, and that's probably what you would have anticipated. So what you end up with here is the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. All right? So to keep it sort of formal, that's what you would do. But then you've got those probabilities up there in the table, so we can substitute in and add them together, and you'd have 0.4 plus 0.11 plus 0.01, and if you add those together, you get 0.52, which is what you're supposed to end up with here. The other compound probability that we're supposed to get is the probability that x is strictly less than 3, but greater than or equal to 1. So you do the same thing. You say, okay, well, what possible values of x are going to satisfy that inequality? 3 is not going to work this time because that's a strict inequality right there. But 1 is going to work because that's a non-strict inequality. So 1 is going to work, 2 is going to work. You just have to add their probabilities together. So 0.48 plus 0.4, you get 0.88. That's the answer. And that's about it. So compound probabilities, not too bad. The next thing that shows up is expected value in the second half of that page. What the expected value is that's the mean of the distribution of the random variable. And the way that you compute it actually is not going to be too bad algebraically. You don't have to really do anything crazy. I suppose it could be long if you had a lot of possible values, but it's not really anything too crazy. So really what you have to do is it's a weighted average of the possible values using the probabilities as the weights. I've got it reproduced on the board now, and I suppose since I have the indexing going from 1 to n, that I have it written for a finite number of possible values, but that is what's going on here. And if you look at the term that you'll get for each individual outcome, which would be this part, so what the individual components of that sum would be. In each case, it's you take the outcome and multiply by its probability, and then you just have a bunch of those products that you have to add together. Now, when you do that, if you've already got the distribution written out as a table, then this becomes really systematic, because then you can kind of just cycle through the columns and you'll get it. And that's exactly what we're going to do. I've got it all written out on the board now. And if you look at what I did, that's basically all that happened. The 1 times 0.48 comes from the 1 and the 0.48 in that first column. Then 2 times 0.4, 3 times 0.11, 4 times 0.01. Since all the values that are inside the parentheses are the respective probabilities related to those possible values of 1, 2, 3, and 4. But then the algebra really isn't too bad. And what you end up with if you simplify this is that you should end up with 1.65. So all those individual products and then add them all together, that's what you should get. So not too bad for the expected value, especially when you only have 4 possible values there. For the example that's on the top of the third page, we're supposed to do the same thing. We're supposed to compute the expected value of the number of imperfections per 10 meters of synthetic fabric. However, it looks like we're missing a probability. That's okay. If we're only missing one probability, we can use the fact that when you add all the individual probabilities together, you have to get 1. So then we should be able to back solve for that and say, well, if we add up all these other probabilities, get that sum, and then subtract it from 1, what we get would be this missing probability right here. And so there it is written out, where if you take all of those probabilities that are already there in the table, add them up, and then whatever that sum is, you subtract from 1, that would have to give you the missing probability. And essentially, you're just using the idea that when you add all of the individual probabilities together, you have to get 1. And now that we have that missing probability, the probability that x equals 1, now we can compute the expected value. And so there it is, using the same sort of methodology that we used for the last one, where now that we know that the probability that x equals 1 is 0.37, then I just went through column by column and said, okay, well, 0 times the probability that x equals 0, but that's 0.41, plus 1 times the probability that x equals 1, which is 0.37, and so forth. You just cycle through the columns, you get those 5 terms, and what you should end up with, if you simplify that, is that you should get 0.88. So that would be the expected number of imperfections per 10 meters of fabric. The other example toward the bottom is short, but there is something that you have to watch out for with that one. What you have to watch out for with that one on the bottom is that you have a possible value that's negative. If you look at what's there in the wording, the two options, the two possible values are a profit of $4,000, that's positive, or a loss of $1,000, and that one's negative. So the possible values aren't 4,000 and 1,000. They're 4,000 and negative 1,000. So that's where you have to be careful sometimes when you have a possible value that's a negative number. But it looks like this wouldn't be too bad to turn into a table because there are only two possible values. You got your 4,000, you got your negative 1,000, and the probabilities are right there in the wording. So probability of 0.25 of the $4,000 profit, probability of 0.75 of the $1,000 loss. So making this table is going to be pretty quick. I've got it up there in the corner now, and notice that right here I've got negative 1,000, not 1,000 as a possible value. But from there, the expected value is not going to be too bad. It's the same idea. We're just going to go through the columns, all two of them, and we'll get it. So the expected value of x here would be 4,000 times 0.25 plus negative 1,000 times 0.75. And if you simplify it, that should be 1,000 minus 750, so it's $250. So that's what you should end up with here, is just $250. And really, I know I'm stressing it a lot, but it's an easy thing to forget about to make sure that that is negative, since it should be, because it's a loss. The next page is about variance, which doesn't come up on the extra credit assignment, but this does go along with expected value. If you're going to have a measure of center, you would have a measure of spread that goes with it. Variance is going to be your measure of spread. So what I'll do is I'll go through the example in a minute for the restaurant, and we'll just kind of talk about it. I'll write everything out without the camera running, and then just kind of point a couple of things out. You can see the example there for the SAT where it's already filled in, where the variance is computed, and then if you want the standard deviation instead of the variance, you just have to take the square root. The other thing that's worth pointing out is that there are two ways of computing the variance. One is to use its actual definition, which is that it's the expected squared distance from the mean, so you would compute it as the expected value of x minus mu quantity squared. I suppose in a way that's the more conventional way of doing it, where then the other way, which is right underneath it, so the second thing up toward the top of the page, is that you could compute it as the expected value of x squared minus the expected value of x quantity squared. That always felt simpler to me in the sense that it felt like there was less algebra, but I suppose that's one of those things where if you have to compute a variance from scratch for a general discrete variable, whichever one feels like it's easier is probably the right one, because you're going to end up in the same place either way. Both options for the computation are on the board right now. The first one, this one right here, this is if you do it as the expected value of x minus mu quantity squared, which you can see right here. There's an x minus mu squared. Right here is an x minus mu squared as well. And so then if you do it that way, what you end up with is 4,687,500. You get the same thing down here. And this one here is doing it as the expected value of x squared minus the expected value of x quantity squared. So there's an x squared, the 4,000 squared. There's an x squared, the negative 1,000 squared. And then there's the minus the expected value of x quantity squared, right? The expected value of x is 250. So there's that being squared and subtracted off. You end up in the same place. If there's anything else that's worth saying about the variance is that its units don't match the units of the initial distribution up here or the expected value. 4,000 and negative 1,000, those are in dollars. The 250 right here, that's also in dollars. However, the variance, because that's the average squared distance from the mean, the units are squared too. So the variance is actually in square dollars, whatever those are. If you would rather have all of the units match, then you want the standard deviation. And another way to look at this is you say, well, the possible values are 4,000 or plus 4,000 and negative 1,000. So this number seems huge. This number seems really, really big compared to those possible values up there. So it seems like this is kind of hard to interpret. But if you take the square root, you end up with a standard deviation, which will be in dollars, just like everything else. Then that becomes a little bit easier to handle. And if you take the square root of the variance, what you get, I think I can squeeze this in on the board down here. So the standard deviation of x would be the square root of 4,687,500. And what you end up with is 2165.06. And that number, when you look at it, you think, okay, that I understand, right? It's in dollars, just like everything else, right? Square dollars is kind of abstract and weird, but dollars, that makes sense. All right, that covers the variance, and now we can get into specific distributions. So there is a lead up to get to the binomial, but it's really short and we need it because the binomial is built out of this other kind of random variable called a Bernoulli. Page 5, we've got the Bernoulli distribution, which is a specific discrete distribution. It's one where there are two possible values. So generally, or I guess generically, they're referred to as success and failure. But anything like a yes or a no, or something to that effect would also certainly work. And if you think of success and failure as being the two possible values, where when we actually get into this, the thing that's the success is generally the possible outcome that you're more interested in. It doesn't have to be the one that's good. It can be the one that's bad. It might be the probability of developing cancer or something, where the outcome that you're interested in is the bad one, not the good one. So the success doesn't necessarily equate with good, but that's okay. We'll get there when we get there. The other thing is the way that the probabilities are customarily labeled, where success is considered to be a 1, failure is considered to be a 0. And if you think, well, that sounds like binary, yeah, that's right. just like binomial, right? Binomial is 2, binary is 2. So yeah, there are going to be 1s and 0s at least for now. When we combine this together to get the binomial, we get some other numbers though. So there's the idea, what I was just talking about, where a success is typically denoted by a 1. So the probability of a success would be the probability that x equals 1, which is right up there. And if that probability is p, then the probability of a failure would have to be 1 minus p, because since there are only 2 possible outcomes, those 2 probabilities would have to add up to 1. Then underneath, we're asked what the expected value should be for a Bernoulli random variable. This is really short. I suppose you could write it out in table form if you wanted to, but I think we can skip it here. The expected value would be, well, your only possible values are 1 and 0, and their probabilities are right there. So this would be 1 times p, right, since p is the probability that x equals 1, plus 0 times 1 minus p. But then this whole term goes to 0, and all you're really left with is just p. So see what I mean? Nice and short. And then the variance would be p times 1 minus p, or p times q. I've got it written as p times q on there because it seemed more elegant, I suppose. But there's nothing wrong with writing it as p times 1 minus p. Some people and some books are going to do it one way, and some people, some books, some references are going to do it the other way. But that we're actually going to need to get the expected value for a binomial in a couple of minutes. Okay, so now the next page, page 6, talks about the binomial, at least introduces it. So instead of just one Bernoulli experiment, which would be anything with 2 possible outcomes, the easiest one to understand is probably flipping a coin. If you flip a coin, either you get heads or you get tails. That sort of thing. Where if you want to view heads as being the outcome that's of interest, then that's your success. And so then the probability of success and the probability of failure are both going to be 0.5, at least in that scenario. But what if instead of one Bernoulli experiment, we have a bunch of repetitions of a Bernoulli experiment? So instead of flipping a coin once, you flip a coin 10 times or 15 times or something like that. Well, then you're going to have a number of trials or a number of repetitions. Where if you're going to flip a coin 10 times, you've got 10 repetitions, right? That part seems pretty straightforward so far. But then that would mean that for each of those repetitions or each of those trials, you're going to have a Bernoulli random variable. So if you do have 10 flips of the coin, then the first flip, maybe you're going to call its variable x sub 1. So using subscripts or differentiation. So x sub 1 for the first flip, x sub 2 for the second, x sub 3 for the third, up to x sub 10 for the 10th. Okay? Well, as before, we're going to assume that the probability of success in a single trial is p, which I guess for flipping a coin it's 0.5, but for a general Bernoulli variable it's p. And the other thing we need for this to work right with the binomial is that has to stay consistent. So from one trial to another, it can't change. Otherwise, this computation will get a lot more complicated. So all that's in that first half of page 6, and then the way that you get a binomial random variable, which is that you add all of the individual Bernoulli random variables together. All right, so we've got x up there that's binomial, and it's defined as being the sum of all those Bernoulli random variables. Okay, well then if we want to get the possible outcomes of x, think about it this way. For each of those Bernoulli variables up there, like for x1, the possible values are 0 and 1. For x2, possible values are 0 and 1. For xn, possible values are 0 and 1. So if you think about it that way, the smallest possible value of x would be 0, because if they're all failures, you get 0 plus 0 plus 0 plus 0 plus 0, right? But then, what if they're all successes? Well, then they're all 1s. You have 1 plus 1 plus 1 plus 1. You have n 1s added together, but that's just n times 1, which is n. So 0 is possible, n is possible, and any integer in between is possible. This is a count, right? It's the number of 1s that you get up there. You can't possibly end up with a fraction. So that's what we know so far. You could get 0, you could get n, you could get any value in between. So the possible outcomes of x, 0, 1, 2, 3, and so forth up to n. And then what is x counting? Well, every time that you add in a 1, you're adding in an instance where there was a success, right? If you have 0, like if x is 0, that means you had no successes. If you had x equal to 1, that means you've got 1 success and the rest are all failures. If x is 2, you've got 2 successes and the rest are all failures. So really what x is counting is the number of successes. So x is counting the number of successes. Okay. Well, then the next thing, toward the bottom of that page, how many different arrangements you could have of a certain number of successes and a certain number of failures. There's a point I want to make about that, which I kind of have to do it out the long way once to get that point across. So the way that I write out what goes in that box on the bottom of the page, it's a mnemonic trick. Don't worry about reproducing it. The point of me doing it is to say this gets really crazy really fast. But I can write it out. It's not really going to be anything too long. So we'll do that first, and then we'll talk about how to do it fast, how to count that up really fast. There we are. We've got them all up there now, all 10 of them. And I just kind of cycled through where the F's were positioned to make sure that I got all of them. The point here is that, yeah, you can do this fast if you know those maneuvers about, okay, if I just kind of keep in my head the way that I'm rearranging where the F's are, it doesn't take too long, but it doesn't take too long here, where that's 3 successes and 2 failures. That's really not a lot. What if you wanted to know how many different ways could you have 15 successes and 9 failures? You're going to have strings that are 24 characters long with 15 S's and 9 F's in there. And to make sure you get them all, that's going to be tough. And even just writing them out is going to take a really long time. So we've got to have a faster way to do this, and we do. And that's what's on the beginning of the next page. The thing that you can use to do this faster is something called a combination, which is defined toward the top of page 7, where this right here, this symbolism inside the parentheses, that's read as n choose k, and it's not n divided by k. That's a really common mistake if you haven't seen this before. And I suppose whether or not you've seen this before depends on what state you went to high school in, because different states are going to have different requirements as far as algebra is concerned, and this is one of those things where some states do it, but not all states do it. So if this is brand new, that's the trap to avoid, is that that's not going to be just n divided by k. In most cases. I suppose there are special cases where that would end up being equivalent, but for the most part, that's not going to be the way that it works out. And when you expand it to where you can write it as a quotient, it ends up being n factorial divided by k factorial times n minus k factorial. So the exclamation point, if you're not familiar with that, that stands for factorial, where like it says on the page, n factorial is n times n minus 1 times n minus 2 and so forth, down to 3 times 2 times 1. So 5 factorial, 5 times 4 times 3 times 2 times 1. 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And by definition, 0 factorial is 1, not 0. If it was 0, it would actually cause all kinds of trouble in what we're about to do. But it's not 0, it's 1. And then there are a few examples there of how to simplify combinations, so we'll go through those. The first one, to simplify 8 choose 5. If you follow along with how you can expand the combination up here and write it as a fraction, what you're going to have is 8 factorial in the numerator divided by 5 factorial since k is 5 here. And then n minus k is 8 minus 5, so it's going to be 3. And then if you expand the factorials, you get this, where 8 factorial, the numerator, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then in the denominator, 5 factorial is 5 times 4 times 3 times 2 times 1, and then the 3 factorial at the end, right over there. Okay, well, when you simplify these, you should be able to cancel out a ton of stuff. Especially when you think, well, if this is supposed to tell you how many different ways you could have k successes and n trials, shouldn't that be an integer? Yes, it should. So you're going to be able to cancel a lot of things. And if I have a suggestion here, it would be this. You can always cancel out one of the factorials in the denominator right away. And then you can kind of work on the other one. What I would do is get rid of the bigger factorial first. So what I mean by that is, look at what we've got down here. We've got 5 factorial and a 3 factorial. I would immediately get rid of the bigger one, the 5 factorial, because there's a 5 factorial, and there's a 5 factorial. So now there's a whole bunch of stuff canceled out. And then with the smaller factorial in the denominator, I would say just get rid of whatever you can by cancellation. So 3 times 2, that's 6. There's a 6, there's a 6. And so what we're left with is 8 times 7, which is 56, divided by 1. So this is really just 56. I think that's how you do it in general. Try to get rid of that big factorial in the denominator first. That'll make the cancellation a little bit faster, I think. The next one, where it's 12, choose 4, we want to simplify that. If you write it out expanded to where it's written as a quotient, that's going to be 12 factorial, since 12 is n, divided by 4 factorial, since k is 4, times n minus k, which is 8, right? 12 minus 4, that's 8 factorial. What I'm going to do here is, since this is going to be so long, if I expand it all the way out left to right, watch how I write out this 12 factorial. I'm going to write it as 12 times 11 times 10 times 9 times 8 factorial. And I'm going to leave it like that, where it's not expanded all the way. The reason I'm doing that is because I'm looking down here. I've got a 4 and an 8, and I'm going after that 8 factorial right away. I'm going to get that out of there. So I'm actually going to cancel that with this in the next step. But I am going to write the 4 factorial all the way out because that's one where I'll just have to kind of see what I can do. So I've got the 4 factorial expanded, but the 8 factorial I'm just going to leave like that because right away I'm just going to go 8 factorial, those are going to cancel out. And then other than that, like I said, do what you can. 4 times 3 is 12, there's a 12 right above it, so we can do that. And then we still got a 2 down here, but the 2 goes into 10 5 times. So 2 goes into 10 5 times. So now we've canceled everything out of the denominator. We got a 1 down there. And the numerator, that's 11 times 5 times 9. So let's see, that's 45 times 11, which would be 450 plus 45, which is 495. So that's what we should get there, 495. The next one is 7 choose 6, which if you expand it out would be 7 factorial divided by 6 factorial times 1 factorial. This one will simplify pretty fast if you use the same kind of maneuver that we just did in number 2, where if you say, I'm getting rid of the 6 factorial. So then you could write the 7 factorial as 7 times 6 factorial and just not write that all the way out, not expand it all the way. That will keep things nice and short because then we can just cancel those 6 factorials. This is 7 over 1, and it's just 7. There's actually a way to see that it's 7 without doing the algebra here. Because you could say, another way of thinking about what a combination will tell you, because we've been thinking about it in the context of a binomial, where we say, well, it'll tell you how many different ways you can have k successes and n trials, and that's true. But it's actually more flexible than that. Another thing that it'll tell you is how many different ways could you pick 6 things out of 7. And if you're picking 6 things out of 7, you're leaving 1 out. How many different ways could you leave out 1 thing? Well, you could leave out the first thing, or the second, or the third, or the fourth, or the fifth, or the sixth, or the seventh. 7 ways you could do it. So anything of that form of n choose n minus 1 simplifies really well. And along similar lines, anything of the form n choose 1. Because think about it that way. If it was 7 choose 1, then what's that going to tell you is how many different ways could you pick 1 thing out of 7? Well, 7. You could pick the first or the second or the third or the fourth or the fifth or the sixth or the seventh. So those actually simplify really fast. They don't always work out quite that nicely, but when they do, you might as well take advantage of it. Number 4, 4 choose 0. It's not 0 and it's not undefined. Those are the traps. But if you expand this, just like we expanded everything else using that formula up there, you'd have 4 factorial over 0 factorial times 4 factorial, like so. And then you'd say, oh, look, there's a 4 factorial and there's another one. Cancel them. And 0 factorial by definition is 1. So really what you've got going on here is 1 divided by 1, which is 1. And if you want to kind of reason your way through this one, you could. Just like with the last one, how many different ways could you pick this number of things out of this number of things? How many different ways could you pick 0 things out of 4? 1. You don't pick any. You could do that, but that doesn't have any other arrangements. So there's one way that you can do it. I suppose Along similar lines, how many different ways could you pick 4 things out of 4? 1, you pick them all, and that doesn't have other arrangements. So 4 choose 4 would be the same thing as this. But if you look at what would happen with 4 choose 4, the only thing that would be different is that the order of these factorials in the denominator would flip. And so yeah, when you simplify, you should get the same thing. Now that we've gone through how the combinations work, we can put the binomial probability function together. And that's what this is. If you look at what's going on here, you've got, and I'm going to start in the middle on purpose just so I can kind of talk about that at the end to sort of do this chronologically. But you've got the probability of success in a single trial raised to the number of successes. You've got the probability of failure in a single trial raised to the number of failures. And then the n choose k, the combination out in front, that takes care of all the different possible arrangements of k successes and n minus k failures. So that would be the function that you would use to compute a binomial probability. And for those examples that are on this page and then the one in the beginning of the next page, that's what we're going to use. So for that example that's there about oils being, okay, based on that example that's there with the oil wells being drilled and 30% of them striking oil, well, we know what the probability of success is in a single trial. It's 0.3 if 30% of them have struck oil based on past data. And then there are 8 wells that are being drilled. We have 8 locations, so presumably for each of those locations there's going to be a well drilled. So there are going to be 8 repetitions here of drilling the well and seeing if you strike oil. So that's going to be our n. P, the probability of success, which would be drilling a well and striking oil in this case, that's going to be 0.3. And with number 1, we're asked to find the probability that exactly 3 of the 8 wells strike oil. Okay? Probability that x equals 3. So here 3 is going to be k. That's our number of successes. If we just substitute straight into the formula, what we're going to have is 8 choose 3 times 0.3 raised to the 3rd power times 0.7 raised to the 5th power, like so. And luckily, we already know what 8 choose 3 is because we already figured it out on the last page. It's 56, right? Sometimes you have to do the work there, and usually you have to do the work there, really. But here, we already did it, so there's no need to do it again. All right, so I did that intentionally just to make the first one a little simpler, but that is just 56 multiplied by 0.3 to the 3rd and then multiplied by 0.7 to the 5th. And this is the point where you're probably going to want a calculator. If you want to do all this by hand, that's really admirable, but it's going to take a lot longer. If you use a calculator here and round to 4 places, what you will get is 0.2541 for the probability that exactly 3 are going to strike oil. In number 2, we want to find the probability that at least 1 strikes oil. And if you go back to the compound probability stuff that we had earlier, I think on the 2nd page, where then you just add up all the individual probabilities that you would need, all the possible outcomes that are going to satisfy this inequality, you can do that here. I don't know if I would. So if you were going to do that here, you'd say, okay, well, if there are 8 wells being drilled, you need the probability that x equals 1, probability that x equals 2, 3, 4, 5, 6, 7, and 8. You're going to add them together. That's a lot of work. And if you're in this situation, you're trying to figure out a compound binomial probability, and if you do all the individual probabilities the way it's set up, and you go, that looks kind of long, see what happens if you use the complement. So what if I did this? That would have to be true because every possible value is either greater than or equal to 1 or less than 1. So this is absolutely correct. But getting this is not a lot of work because there's only one possible value that's strictly less than 1, and that's 0. So this becomes 1 minus the probability that x equals 0. So in this particular case, if I use the complement here, I have to get 1 probability instead of 8. So I'm going to use the complement here. And this one is really not too bad. So the probability that x equals 0, let's see, that would be 8 choose 0 times 0.3 raised to the 0 power times 0.7 raised to the 8th. Okay, well, 8 choose 0, just like 4 choose 0, is going to end up being 1. You can expand it if you want to, or you can just think, well, how many ways could you pick 0 things out of 8? 1. You don't pick any. That's it. This term right here is also a 1, since anything raised to the 0 power is going to be 1. So what are we ending up with? We're going to have 1 times 0.7 to the 8th for the probability that x equals 0. So this is really just 1 minus 0.7 to the 8th, and what you end up with is 0.9424. You will get the same thing if you do this directly, where you get the probabilities that x equals 1, 2, 3, 4, 5, 6, 7, and 8 and add them together. That will work. It will also be a lot longer. So that's what I would suggest if you have a probability that looks like it's going to be long, if you're going to do it directly. At least take a look at the complement, right? It's worth a look. Maybe the complement's short, like it is here. However, with number 3, the complement isn't going to be shorter. It's actually going to be shorter to do it directly, where we want the probability that more than 5 strike oil. Well, there are only 8 total. So more than 5 would be 6, 7, and 8. Those are going to be the possible outcomes that are going to satisfy that strict inequality right there. So we're going to have the probability that x equals 6 plus the probability that x equals 7 plus the probability that x equals 8. That's not really short, but it's not really long either. And if you use the complement here, that's actually going to bite you because that's going to be longer. Because if you use the complement, 1 minus the probability that x is less than or equal to 5, then you got 0, 1, 2, 3, 4, and 5. Here, just 6, 7, and 8. So this time going directly is actually shorter. I took the liberty of going ahead and just writing these out with all the numbers substituted in. So there's the probability that x equals 6. There's the probability that x equals 7. There's the probability that x equals 8. And I know what those combinations are going to simplify to as well. This one's not too bad. It looks like what you should end up with there is 28. So you'd have 28 times 0.3 to the 6th times 0.7 squared. 8 choose 7 is going to be 8, right? How many different ways could you pick 7 things and leave one out? So it's just going to be 8 times 0.3 to the 7th times 0.7. And then 8 choose 8 is going to be 1. How many different ways could you pick 8 things out of 8? 1, you pick them all. So you have 1 times 0.3 to the 8th, and then I suppose times another 1, since that 0.7 to the 0, anything to the 0 power is going to be 1. And let's see, I do have these rounded off to the nearest 10,000th, so I guess I can write those in and then put in the final answer. Well, let's see, the probability that x equals 6 is 0.0100 to 4 places. Then for 7, it's 0.0012. Then for 8, it's 0.0001. And if you add those together, you get 0.0113. So that's where we are right there, 0.0113. So this isn't too bad. It's 3 binomial probabilities, 3 individual ones that you have to add together. So it's not the shortest thing in the world, but it's not the longest thing in the world. If this is as bad as it gets, this still is absolutely doable, right? This really isn't anything insurmountable. You just have to kind of break it down and do them one by one and say, okay, I can do that one by itself. I can do that one by itself. I can do that one by itself. And then just think about it that way. And then once you've got them simplified down, just add them together. Toward the bottom of that page, I guess really it's the last 2/3, but the examples are toward the bottom of the page. We have center and spread, so the expected value and the variance standard deviation. You can do the expected value and the variance the long way being what you would do for a general discrete variable. If you really want to do that, if you think it's fun, you can go right ahead. But if you want to do it faster for a binomial, there is a way. So because with the Bernoulli distribution where the expected value there was p, basically what you end up with for a binomial is that you have p for every component of that binomial variable, where we had x written as x1 plus x2 plus and so forth up to xn. The expected value for x1 is p, for x2 it's p, for x3 it's p, up to for xn it's p. So it's n times p. So for a binomial, that will get you where you need to be. And that means that for the oil example, the expected value is just 8 times 0.3, which is 2.4. And that's that. There's nothing else that you have to do. You could make this longer. You could get all of the individual probabilities, like the probability that x equals 0, 1, 2, 3, 4, 5, 6, 7, and 8. And then you could do the expected value as a weighted average using the probabilities as the weights like we did before. That will work. It's a whole lot longer than this. So we've got that for the expected value, nice and short. And then the variance and standard deviation, they're going to be short too, because the variance, like it says there on the page, it's just n times p times 1 minus p. So for this example, it's 8 times 0.3 times 0.7, which is 1.68. And then if you would prefer to have the standard deviation instead of the variance, you just have to take the square root. So the standard deviation would be the square root of 1.68, which when you take that square root, let's see, 1.2961. All right. Before looking, I would have guessed it was close to 1.3. I'm kind of proud of myself. All right, so that takes care of the manual computation stuff. The last page covers how to do things using R, although there is one thing we have to go through first before we actually get R up on the screen. Here are the R functions that show up on page 10, where if you want the probability of a specific number of successes, so the probability that x equals k, so meaning like the probability that x equals 12, or the probability that x equals 5, or the probability that x equals 2, you want to be up here. So D binom would give you what you want. But if you have some sort of inequality, so here we have the probability that x is less than or equal to k, so that's a cumulative probability because it includes k and everything that comes before it, right? Just like a cumulative exam. It includes the new stuff plus all the old stuff, like that. So if you're going to do that, you're going to want p binom. This is going to be the more useful function because that will typically get you around more computation, right? It might get you around some big, long computation, and this one typically doesn't. Maybe if you have, I guess, sort of an obnoxious-looking combination, it would get you out of doing that, but really this one is going to be the one that's more useful. However, you've got to have your inequality written with less than or equal to's in it, or a less than or equal to, I suppose, depending on if you have a compound inequality or a single inequality. So you might have to do a little bit of maneuvering at first. And so that's what we're going to have to do with at least the third example that's on here. So part C, we're going to have to do a little bit of maneuvering there. All right, so just going through this in words. That first one in the example where it's about the diner and how many customers order a drink other than water with lunch, and we want to figure out what these probabilities are going to be out of 12 customers. So the first is the probability that 8 order a drink with lunch. So that's exactly 8. And so that means the thing that we're trying to get is the probability that x equals 8. Okay. Well, then what about in part B, the probability that no more than half order a drink with lunch? Well, half of 12 is 6, and we don't want to go above that, so we don't want to include 7, 8, 9, 10, 11, or 12. We do want to include 6, right? 6 is exactly half. It's not more. So the probability of no more than half would be the probability that x is less than or equal to 6. So looking at what we've got so far, part A is set up for D binom. So if we're going to do it, and I'll add this into the video in a second, but it would be D binom with 8 for the k, then 12 for n, and then 0.7 for p. And that would do it for you. Here, this is set up for p binom because it's got a less than or equal to it. So this should be p binom with 6, 12, and 0.7. I should point out, I suppose, that you could, instead of using p binom here, you could use a sum of a bunch of d binoms. So you could have d binom with 0 as the first argument, plus d binom with 1 as the first argument, and then with 2, 3, 4, 5, and 6. That's a lot of extra work. It's easier just to use p binom. C is when we're going to move things around a little. because we're asked for the probability that at least 10 ordered or wrinkled lunch. So at least is a greater than or equal to. Like so. But that's not the kind of inequality that we want. So we've got to rearrange things a little bit. And I guess the first thing that would be a good idea, I would think, would be to say, well, if you use the complement, that would at least give you a probability where the inequality went in the opposite direction. That's a good start. So if we do that, this would be 1 minus the probability that x is less than 10, strictly less than 10, right? Because these two probabilities have to add up to 1. Every possible value that you could get is either greater than or equal to 10 or strictly less than 10. This is close. But we need an expression with a less than or equal to in it, not a strict less than. But because this is a count, there's something between 9 and 10. Strictly between, right? There's no 9.5. There's no 9 3/4. So what we could do here is we could say this is the same thing as 1 minus the probability that x is less than or equal to 9. That's how you do it. Because if you look at this part of it, you go, oh, it's got a less than or equal to in it. We can use p binom now. We can. So you could write this one out as 1 minus p binom, where the arguments are 9, 12, and 0.7. And that will do it. So the next thing that's going to happen, and I'll have to splice videos together to get this to work, but I'll add in actual screenshots.